Am I watching a heart being printed? Live? In front of my eyes? How did we get here? Let's start from the beginning. Stop. Perfect. 1439. Gutenberg invents the first printer, with ink and a screw press that's changed everything, basically transforming how we share knowledge, nothing less. Since then, the world has seen electricity, computers, software, important building blocks that brought us to 1983. Charles Hall creates the first additive manufacturing machine, commonly called 3D printing. At the time, it seems limitless, bringing ideas to life layer by layer. The only limit is your imagination, they said. Or was it? Not really. Back then, 3D printing was still a bit clunky for high-stakes industries like biomedical. They needed higher standards. 5 years later, the first light-based 3D printer was born. Powerful lasers, LCD screens, and UV lights. Suddenly, 3D printing got more speed and accuracy. And in 2003, things got wild. Bioink was created, a material packed with living cells. Printing organs, creating human tissues, biofabrication was now possible. 2024.
Behind me is a new technology that we've been working on, a new type of biofabrication technology.
Dynamic Interface Printing, or DIP, was published in Nature under the same title. No more layer-by-layer process. DIP can directly solidify the bioink. Right now you're watching a small heart being printed, in real time. Watching this unfold feels like magic, doesn't it? So, how does it work? The printer head dives in the container filled with bioink. Once it reaches the bottom, air is pressurized inside the nozzle, creating at the tip an air-liquid boundary. Powerful lasers then travel through air in the tube, create a specific pattern, and solidifies bioink. This solidification happens at the meniscus right here. It's that tiny curved line created by the surface tension between air and liquid. Acoustic vibrations are used to keep the meniscus steady. These setups make it possible to create instant shapes. It can already produce cartilage, denser bones, and gels that act like organs. Why is it exciting? It brings unmatched speed and precision in biofabrication. The revolution here is keeping a laser in the tube filled with air until it reaches the material, eliminating light scattering problems. The result is stunning. DIP is 350 times faster than other bioprinting methods. And there's more. Those other methods rely on natural cells alignment, which often fail to reproduce human tissues.
The difference with our system is that we're able to embed cells within the structure that mimic the tissues that are found in our bodies.
He's not just built the world's fastest 3D printer, he's built the most suitable printer for 3D bioprinting applications that the world has seen.
But this technology has limits. It's only effective for objects under 10 mm wide. The next big challenge is clearly to scale things up. Another critic is the media coverage. I was interested at first on the paper about his potential on space missions. The problem? There's not a single mention about microgravity in the study. It might work thanks to the surface tension on the meniscus, but it will take way more development before becoming reliable in orbit. After having seen the evolution of printers, do you think DIP will transform industries? Or is it just the start of something even bigger?